Basic principles of pass transistor circuits. The fundamental building block of an NMOS dynamic logic circuits consisting of an NMOS pass transistor driving the gate of another NMOS transistor is shown in figure. As already discussed in example, the pass transistor MP is driven by the periodic clock signal and acts as an access switch to either charge up or charge down the parasitic capacitance Cs depending on the input signal Vin. Thus, the two possible operations when the clock signal is active Ck equal to 1 are the logic 1 transfer charging up the capacitance Cs to a logic high level and logic 0 transfer charging down the capacitance Cs to a logic low level. In either case, the output of the depletion load NMOS inverter obviously assumes a logic low or logic high level depending on the voltage Vs. Notice that the pass transistor MP provides the only current path to the intermediate capacitive node soft node X when the clock signal becomes inactive Ck equal to 0. The passed transistor ceases to conduct the charge stored in the parasitic capacitor. Cx continues to determine the output level of the inverter. In the following, we will first examine the charge up event. As you can see in the figure, the basic building block for NMOS dynamic logic, which consists of an NMOS pass transistor driving the gate of another NMOS transistor. Equivalent circuit for the logic 1 transfer event. Logic 1 transfer. Assume that the soft node voltage is equal to 0 initially, that is Vx t equal to 0 equal to Vx t equal to 0 equal to 0 volts. A logic 1 level is applied to the input terminal, which corresponds to Vin equal to VOH equal to VDD. Now the clock signal at the gate of the pass transistor goes from 0 to VDD at t equal to 0. It can be seen that the pass transistor MP starts to conduct as soon as the clock signal becomes active, and that MP will operate in saturation throughout this cycle since VDS equal to VGS. Consequently, VDS is greater than VGS minus VTN. The circuit to be analyzed for the logic 1 transfer event can be simplified into an equivalent circuit as shown in figure. The pass transistor MP operating in the saturation region starts to charge up the capacitor Cx. Thus, Cs dVx by dt equal to Kn by 2 VDD minus Vx minus VTN whole square. Note that the threshold voltage of the pass transistor subject to substrate bias event and therefore depends on the voltage level Vx. To simplify our analysis, we will neglect the substrate bias effect in this point. In integrating, we will obtain integrals 0 to t dt equal to 2 Cx by Kn integrals 0 to Vx dVx by VDD minus Vx minus Vt comma n whole square equal to 2 Cx by Kn 1 by VDD minus Vx minus Vt comma n 0 to Vx equal to 2Cx by Kn 1 by VDD minus Vx minus V3n minus 1 by VDD minus V3n. Here in this figure, the variation of Vx as a function of time during logic 1 transfer. This equation can be solved for Vx of t as follows. Vx of t is equal to VDD minus Vtn Kn VDD minus Vtn by 2Cx into t by 1 plus Kn VDD minus Vtn by 2Cx into t. The variation of the node voltage Vx according to equation is plotted as a function of time in figure. The voltage rises from its initial value of 0 volts and approaches a limit value for large t, but it cannot exceed its limit value of Vmax equal to VDD minus Vtn. The pass transistor will turn off when Vx equal to Vmax, since at this point its gate to source voltage will be equal to its threshold voltage. Therefore, the voltage at node X can never attain the full potential supply voltage level of VDD during the logic 1 transfer. The actual value of the maximum possible voltage Vmax at node X can be found by taking into account the substrate bias effect for MP. Vmax equal to Vx t tends to infinity equal to VDD minus Vtn equal to VDD minus V T naught n minus gamma root over mod 2 phi f plus Vmax minus root over mod 2 phi f. Thus, the voltage Vx which is obtained at the node X following a logic 1 transfer can be considerably lower than VDD. Also note that the rise time of the voltage Vx will be underestimated if the zero bias threshold voltage Vt0 is used in equation. In that case, the actual charge up time will be longer than predicted by equation because the drain current of the NMOS transistor is decreased due to the substrate bias effect. The fact that the logic voltage Vx has an upper limit of Vmax equal to VDD minus Vt and has a significant implication for circuit design. As an example, consider the following case in which a logic 1 at the input node Vin equal to VDD is being transferred through a chain of cascaded pass transistor figure. For example, for simple analysis, we assume that initially all internal node voltages V1 through V4 are 0. The first pass transistor M1 operates in saturation with VDS greater than VGS1, VDS1 greater than VGS1 minus VTN1. Therefore, the voltage at node 1 cannot exceed the limit value Vmax1 equal to VDD minus VTN1. Now, assuming that the pass transistors in this circuit are identical, and the second pass transistor M2 operates at the saturation boundary. As a result, the voltage at the node 2 will be equal to Vmax2 equal to VDD minus VT and 2. It can be easily seen that with VTN1 equal to VTN2 is equal to VTN3, so on, the node voltage at the end of the pass transistor chain will become one threshold voltage lower than VDD. Regardless of the number of pass transistors in the chain, it can be observed that steady state internal node voltages in this circuit are always one threshold voltage below VDD regardless of the initial voltages. Now, consider a different case in which a output of each pass transistor drives the gate of another pass transistor as depicted in figure. Here, the output of the first pass transistor M1 can reach the limit Vmax1 is equal to VDD minus VTN1. This voltage drives the gate of the second pass transistor, which also operates in the saturation region. This gate to source voltage cannot exceed the VTN2. Hence, the upper limit for V2 is found as Vmax2 equal to VDD minus VTN1 minus VTN2. It can be seen that in this case, each stage causes a significant loss of the voltage level. This amount of voltage drop at each stage can be approximated more realistically by taking into account the responsibility substrate bias effect, which is different in all cases. VTN1 equal to VT0 n minus gamma root over mod 2 phi f plus Vmax1 minus root over mod 2 phi f. VTN2 equal to VT0 n minus gamma root over mod 2 phi f plus Vmax2 minus root over mod 2 phi f. The preceding analysis helped us to examine important characteristics of the logic 1 transfer event, which we will examine in charge down event, which is also called a logic 0 transfer. Figure node voltages in a pass transistor chain during the logic 1 transfer. Figure node voltages during logic 1 transfer when each pass transistor is driving another pass transistor. Logic 0 transfer. Assume that the soft node voltage Vx is equal to logic 1 level initially, that is Vx t equal to 0 equal to Vmax equal to VDD minus VT, and a logic 0 level is applied to the input terminal, which corresponds to Vin equal to 0 volt. Now the clock signal at the gate of the pass transistor goes from 0 to VDD at t equal to 0. The pass transistor MP starts to conduct as soon as the clock signal becomes active, and the direction of the drain current flow through MP, which will be opposite to that during the charge up logic 1 transfer event. This means that the intermediate node X will now correspond to the drain terminal of MP, and that the input node will correspond to its source terminal with VGS equal to VDD and VDS equal to Vmax. It can be seen that the pass transistor operates in the linear region throughout this cycle. This VDS less than VGS minus VTN is the circuit to be analyzed for the logic 0 transfer event can be simplified into an equivalent circuit as shown in figure. As in the logic 1 transfer case, the depletion load NMOS inverter does not affect this event. The pass transistor MP operating in the linear region discharges the parasitic capacitor CS as follows: minus CS VD minus CS dVx by dt equal to Kn by 2 into VDD minus VTN Vx minus Vx square. Vt is equal to minus 2 Cx by Kn into V into dVx by 2 into VDD minus Vt and Vx by minus Vx square. Yes, minus Vx square. Note that the source voltage of the NMOS pass transistor is equal to 0 volts during this event. Hence, there is no substrate bias effect for MP. VTN equal to VT0 N, but the initial condition Vx t equal to 0 equal to VDD minus VTN contains the threshold voltage with substrate bias effect, because the voltage Vx is set during the preceding logic 1 transfer event. To simplify the expression, we will use VTN in the following integrating both sides of equation yields integral 0 to t dt is equal to minus 2 Cx by Kn integral VDD minus VTN Vx 1 by 2 VDD minus VTN by 2 VDD minus VTN minus Vx plus 1 by 2 VDD minus VTN by Vx whole dVx t equal to Cx by Kn VDD minus VTN in natural log of 2 VDD minus VTN minus Vx by Vx Vx from VDD minus VTN to Vx. In this figure, you can see equivalent circuit for the logic 0 transfer event. In this figure, you can see variation of Vx as a function of time during logic 0 transfer. Finally, the fault time expression for the node voltage Vx can be obtained as t equal to Cx by Kn VDD minus VTN natural log 2 VDD minus VTN by minus Vx by Vx. The variation of the node voltage according to is plotted as a function of time in figure. It is seen that the voltage drops from its logic high level of Vmax to 0 volt. Hence, unlike the charge up case, applied input voltage level logic 0 can be transferred to the soft node without any modifications. This event, the fall time T fall for the soft node voltage, Vx can be calculated from equation as follows. First, define the first two time points T 90% and T 10% as times at which the node voltage is equal to 0.9 Vmax and 0.1 Vmax respectively. These two time points can easily be found by using T 90% is equal to Cx by Kn VDD minus Vtn natural log 2 minus 0.9 into VDD minus Vtn by 0.9 VDD minus Vtn is equal to Cs Kn VDD minus Vtn natural log 1.1 by 0.9 T 10% Cs by Kn VDD minus Vtn natural log 1.9 by 0.1. The fall time of the soft node voltage Vx is by definition the difference between T10% and T90%, which is found as tau fail is equal to T10% minus T90% is equal to Cs Kn VDD minus Vtn natural log 19 minus natural log 1.22 equal to 2.47 Cs Kn VD minus Vtn. Until this point, we have examined the transient charge up and charge down events. Which are responsible for logic 1 transfer and logic 0 transfer during the active clock phase, that is when Ck equal to 1. Now we will turn our attention to the storage of logic levels at the soft node X during the inactive clock cycle, that is when Ck equal to 0. Charge storage and charge leakage. As already discussed qualitatively in the preceding session, the preservation of a correct logic level at the soft node during the inactive clock phase depends on preserving a sufficient amount of charge in Cs despite the leakage currents. To analyze the events during the inactive clock phase in more detail, consider the scenario shown in figure below. We will assume that a logic high voltage level has been transferred to soft node during the active clock phase and that now both the input voltage Vin and the clock are equal to 0 volt. The charge stored in Cs will gradually leak away, primarily due to the leakage currents associated with the pass transistor. The gate current of the inverter driver transistor is negligible for all practical purposes. Figure shows a simplified cross section of the NMOS pass transistor together with lump node capacitance Cx. We see that the leakage current is responsible for, here you can see the figure, charge leakage from the soft node. Here you can see the figure simplified cross section of the NMOS pass transistor showing the leakage current components responsible for draining the soft node capacitance Cs. Here you can see the figure equivalent circuit for analyzing the charge leakage process. Draining the soft node capacitance over time has two main components, namely the subthreshold channel current and the reserve conduction current of the drain substrate junction. I leakage equal to I subthreshold MP plus I reverse MP. Note that the certain proportion of the total soft node capacitance CS is due to the reverse bias drain substrate junction, which is also function of the soft node voltage Vs. Other components of CS, which are primarily due to auxiliary related parasitics, can be considered constraints. In our analysis, these constant capacitance components will be represented by C in figure. Thus, we have to express the total charge stored in the soft node as the sum of two main components as follows: Q equal to Qj Vx plus Qin, where Qin equal to Cin into Vx. Cn equal to Cgb plus C poly plus C metal. The total leakage current can be expressed as time derivative of total soft node charge Q. I leakage equal to dq by dt is equal to dqj Vx by dt plus dq in by dt equal to dqj Vx by tdx into dvx by dt plus cn vdx by dt, where dqj Vx by dvx equal to cj Vx equal to a into cj naught by root over 1 plus Vx by phi naught equal to a into root over q phi si na by 2 phi naught plus Vx. According to equation, and phi naught equal to kt by q natural log nd into na by ni square, cj naught equal to root over q xi si na nd by 2 na plus nd phi naught, similar to root over q xi si na by 2 phi naught. Also note that the subthreshold current in deep submicron transistors can significantly can't exceed the reverse current, especially for VDS equal to VDD. In long channel transistors, the magnitude of the subthreshold current can be comparable to that of the reverse leakage current. The reverse conduction current in turn has two main components: the constant reverse saturation current I0 and the generation current Igen, which originates in the depletion region and is a function of the applied bias voltage Vx. To estimate the actual charge leakage time from the soft node, we have to solve the differential equation given in equation. Taking into account the voltage dependent capacitance components and the non-linear leakage currents, for quick estimate of the worst case leakage behavior. On the other hand, the problem can be further simplified. Assume the minimum combined soft node capacitance is given as CS min equal to CGB plus C poly plus C metal plus CDB min, where CDB min represents the minimum junction capacitance obtained under the bias condition Vx equal to Vmax. Now we define the worst case holding time T hold as the shortest time required for the soft node voltage to drop from its initial logic high value to the logic threshold voltage due to the leakage. Once the soft node voltage reaches the logic threshold, the logic stage being driven by the node will lose its previously held state. T hold equal to delta Q critical min by I leakage max, where delta Q critical min equal to Cs min V max minus VDD by 2. The calculation of the worst case leakage time can be simplified with the approximation as will be shown in the following example. Consider the soft node structure shown in the next page, which consists of the drain or source depending on the current direction. Terminal of the pass transistor connected to the polysilicon gate of an NMOS driver transistor via a metal interconnect. Thank you.